So now let's look at our labs now. If you see, first of all, we are going to load these libraries, the mass library, the core plot, and tidyverse. If you don't have them installed, you make sure you install it. So let's load and inspect this particular data set now. So this is the birth weight data set, and we are going to be loading it also from the mass package. Now what we're going to do now, we are going to have a view of this particular birth weight data set. This mutate function is from the dplyr package in the tidyverse. So I've explained more about this in my course, Exploratory Data Analysis with R. So we are going to be changing this particular race to a factor. That is why we are using the mutate function. And smoke also, we are going to be making it a factor. HT, we are going to be making it a factor, and UI, we are going to be making it a factor. So let's even check about the data to see more about these particular factors. So you can see that HT means history of hypertension. UI is the presence of uterine irritability. So this is what we are going to be doing. So let's have a look at our current birth weight variable. So this is what we have. As you have seen, we have already made these 4 as factors, 1, 2, and also race and smoke. So now for the correlation analysis now, conduct the correlation analysis now between variable BWT. So variable BWT is the birth weight in grams, and also the mother's weight. We want to conduct a correlation analysis between these two to see if they are correlated to each other. We're using the COR function for correlation, and we have an argument here, which is the where we can give in the method, which either using Pearson or Spearman. So I'm going to store this in the variable correlation Pearson, and you can see I have a correlation value of 0.19, approximately 0.19. So this value means that there is a weak positive correlation between the birth weight of the baby and that of the mother. So even though sometimes it's possible that as the birth weight increase, the mother's weight increase. So that's what it's meaning in this particular scenario. So let's conduct that of the Spearman. So the Spearman now, I'm going to be using the Spearman argument, the same line of code. So for that of the Spearman, we have 0.06, also signifying a weak positive correlation. So this is it for the correlation analysis, and these are scatter plots now for low birth weights, for the mother's weight and the baby's weight. So we are going to plot in a scatter plot for it. So I'm just using the plot function. I'm not using the ggplot too. This is another way of plotting. I'm just using the plot function. You can see that the scatter plot is somehow scattered, which is showing that there is no, but you can see the direction of the scatter plot is like it's going up. If you can look at it, though the scatter plot is somehow scattered, dispersed, so which means weak positive correlation. And because it's also close to 0, the correlation, you can see that it's almost tending to no correlation at all. I can even interpret it as that. So for the simple linear regression now, this is just a simple linear regression. I'm going to predict a baby weight based on the mother's weight. We use the LM function, and our predictor is given on the left hand side, which is the baby's weight. The mother's weight is on the right hand side, and we use this tilde to show that this is going to predict this. And we give our data, which is the birth weight data. So you can see when you run this now, this summary is going to give you all the model metrics. You can see the coefficient that we have 0.0 this is the coefficient 4.429, and this p-value shows whether that coefficient is significant or not significant. So this is something you have to take note of. So these various asterisks is the various level of significance, as you can see. So most of the times you can use the 0.01 level of significance, which is what is signified by this. You can see, and this is the intercept, also level of significance at this particular level of significance. So at 0.01 level of significance, the mother's weight is significant, which means that an increase in the mother's weight will cause a 4.429 increase in the baby's weight. So this is how we can interpret our simple linear regression. Also, we can plot the regression line using the plot function, where we give in the vector of the mother's weight, then the vector of the baby's weight. We give our main lab, X lab, and the Y lab. So I'm going to plot this now, and you see we have what we call AB line. So this is the regression line. As you can see, it is the line we plot. Most of this what you are now seeing here is the plot of the mother's weight against the birth weight, and this is our regression line. Now for the multiple linear regression, I'm going to be adding more predictors. I'm going to be adding age, and I'm also going to be adding smoking. So smoking status. I can see when I also run this, you can see that I have smoking 1. So for smoking is actually a categorical variable, while age and the mother's weight are both continuous variable. So you can see for that of the age, it is not significant. It's above 0.05 and also other level of significance. But for the mother's weight and the smoking status, they are both above 0.01 level of significance, which means it is what? Significant. So this smoking status is actually various. We have 0 and we have 1. So smoking 1 means the person is smoking, while smoking 0 means the person is not smoking. It's a dichotomous variable. So what this means is that any mother that is smoking, then our birth weight, the birth weight of our child is going to decrease by minus 269.257. Any mother that is smoking. So only one of the, if we have 3 values in a categorical variable, you're going to be seeing 2 here. We are going to compare it with what we call the reference variable, which is now in this situation not smoking. So for example, now you can have low, average, high. So I'm going to be seeing only coefficient of average and high, which will go to the reference variable of low. So that is how you can explain categorical variable here. So this is going to tell you that anybody that is smoking, the birth weight of the child is going to be lower than that of the person that is not smoking by minus 269.257. So these are the various ways of checking for the assumptions after you have plotted your model to see if your residuals, because now we already have the model, we can predict our values. So first of all, I'm going to be plotting the fitted values from my model. You can get it from your model by using the dollar sign to get the fitted values. And also residuals is a function we are going to be applying on the multiple LM to get the residuals. So when I run this, so you can see these are my residuals. So these residuals, these are my fitted values, and this is the residuals. So residuals and fitted. So you can now see that this line is straight line, which means that what? The residuals are normally distributed. So these are you check for the linearity of the residuals and fitted values plots. You can see we are checking for the linearity of the residuals and the fitted values. So fitted values are the values that you have using your model, while the residuals is the difference between the actual values and the fitted values. So we have normality check, which is QQ plots. This is the QQ norm plot and the QQ line. So you can see also our data is also normally distributed. So the various ways of checking for the assumptions. So let's find out the coefficient of determination. It was also inside. You can see we have an R square of 0.05331. This is for our second model we did earlier on, which means that 5% of the variation in the birth weight variable is explained by predictors in the model. This is a very low score, so which means we need to add more factors to get high. So if you look at this, we have two adjusted R square and the R square. Most of the times, it's usually encouraged to use the adjusted R square because sometimes the R square have its disadvantages, because at times you could increase the number of predictors and it's just going to be increasing, even though sometimes the predictors might not be significant. But the adjusted R square, even if you add 5 or 6 predictors that are not significant, the value is not going to change. It's going to be as it is, except if you add a significant predictor. So the higher the number of predictors that are significant, the higher the adjusted R square. But the R square will increase regardless of whether the predictor is significant or not. So it's always good to always use the adjusted R square. Even though in this situation our adjusted R square is low and we need to increase the factors to have a better high score. And for the logistic regression now, what we are now going to be predicting now, we are going to create a binary outcome now for low birth weight, that if it is less than 2,500 grams or otherwise. So now this time around we're still using the same situation earlier on, but this time around we're categorizing low birth weight if the weight is less than 2,500, and any other weight above that is going to be high. So we create this variable, and we're now going to be using this particular variable now, low birth weight, as the outcome variable, and still the same thing we did earlier on, LWT plus smoke. So why I'm just using LWT plus smoke is just to, since we already know the age is not significant from the previous model we did for the linear regression, and I'm going to be using the binomial family because we have two values inside two categories in our outcome variable. low and high birth weight. So if we have multiple, let's say more than 2, then we could use the multinomial. Then I'm just going to summarize the logistic model. So you can see we have various metrics here, but we're just interested in the estimates. So now you can see we have the estimates, but in terms of logistic regression, we're interested in the odds ratio. That's what we're going to use to interpret. So first of all, we have to check for the significance. So I say that 1% level of significance, you can see that this particular two are significant, just like the previous what we had earlier on. So now let's calculate the exponential. So because we don't get it from the model, I already put a formula here to calculate the coefficient of odds ratio by taking the exponential of the coefficient of the logistic model. So you just do this and you can see the intercept, the mothers weight, and the smoking status. What this means is that mothers with high birth weight have 0.987 odds of having children with low birth weights when compared to those with lower birth weight. So the higher the birth weight of the mother, then the odds of her having a child with a low birth weight is 0.99. You can see this is what less. So they have a very lesser odds. So assuming it was more than that now, we could say that, let's say assuming it was more than 1, we could say the odds is very high. So which means they have a lower odds of having a child with what low birth weight. Since our success in this situation now is low birth weight, because we represent it as 1 if the weight is less than 2,500. While for smoking status now, you can see the odds of having children with low birth weight is 1.97 high for those mothers that are smoking compared to mothers that are not smoking, which is also similar to what we had in the linear regression. So this is it for the regression, both the linear and the logistics. And in the future, I'm going to be creating separate courses and go deep into these various techniques and also talk about multinomial.